having a socket. And by means of those sockets, the two programs can address each other. In other words, if one program wants to communicate with another, it will say exactly which program it wants to communicate with by giving the address of that socket. So we have already talked about that. So you need to know how to create a socket and what parameters should go with the socket. Now, I also talked about connect. So on the client side, you connect to a specific socket. So if a client wants to communicate with a server, they must use the connect command to connect with that particular server. And I mentioned last time that in the connect command, you must issue the address of the peer application you want to talk to. You must give the address of their socket. So if it has a composite address like X and Y, X being for the IP address and Y being for the port number, the connect command must contain X and Y. Of course, it's not as simple as that. Once you begin to explain how each of these commands work, you will realize it's a lot more complicated than that. But conceptually, connect enables a program to connect to another socket. So on the client side, at the moment, those two we already know. So the client will create a socket and then say which server they want to connect to. Now, on the server side, we said that the server is always up and running. And by the time a client connects to a server, the server is waiting. The server is in the listen mode. They are waiting. And what are they waiting for? They are waiting for those requests for connection. So if you look at this diagram, you realize that at the point the client, at this point where the client is connecting to the server, that is a connection request. So in other words, what is the server waiting for? The server is waiting for a request for connection. But before it reaches the point where it waits for connection requests, it has to also first create a socket. And then it must use the bind command to give that socket an address. Now, why is it that the server must give the socket an address? Because we said that the method that is used in on the internet gives all the servers well-known addresses, because one of the questions we asked ourselves was, how does the client know the address of all the servers it wants to talk to? So we gave several methods. Now, the one that is typically used on the internet is the one that requires all servers to have well-known addresses. And by the way, if by now you have not looked up those well-known addresses, I think you are doing yourself a disfavor. So please, after this class, go and look up those well-known addresses for all the servers that are well-known. That is the web server, the email server, the DNS server. There are several well-known servers on the internet. Just find out which are these well-known servers and what address, what is the well-known address. So I mentioned, for example, all web servers, they run on port number 80. All the email servers will run on a certain port number and so on and so forth. So when a server has created a socket, they must bind that address to that socket. So if it's a web server, it will bind a port number 80 to its socket. So that's the reason for that bind command. So by the time we have socket and bind, the socket has an address. On the client side, we said you don't need to bind an address because usually the operating system will select a port number. Because at this point, the only thing you need to really select is a port number. The address of the machine on which the program is running is already well known. It's only the port number that has not been allocated. So on the client side, usually the operating system will do that. Because if you're running many programs, it's likely you can choose a port number that's already been chosen. So it's best to leave it to the operating system, which knows all the port numbers of the programs running on that computer, and so will allocate for your program one that is not already being used. So there's a range of numbers you can select port numbers from. For the servers, there's a specific range of numbers for all the well-known servers. Now, for the client side, there's also a range of numbers. I think if you look it up, you'll find out what is the range of numbers for client side and the range of numbers for the well-known servers. Of course, like the programs you are running, the programs you are writing, you will create a server, but it will not be one of those well-known servers, well-known ports, servers with well-known ports. So you will just select an address for your server of your choice. So unless it's a well-known server, it can choose an address by itself. Now, once that has happened, then it needs to use the listen command. What is the purpose of the listen command? The purpose of the listen command is to state or specify how many connections it is willing to have in the queue. Remember, we said when a request arrives on the server side or even on the client side, it is normally put on a queue. So it's really specifying the length of that queue. How many requests could possibly be waiting in a queue at any given time? So it can say, I want the queue to always have 10 requests waiting, or 3 or 2. It just depends on what you think is best for your program. So after the listen, you already have a port that is ready to receive requests. And the request you are receiving is for connections. Remember, it is for connection. So the way that a server says it is willing to receive a request, remember it has created a queue and there's nothing in that queue at the moment. So if it issues an accept, there will be no request because no client has already connected. So the accept command, remember, is a blocking command. You must remember that. This is a blocking command. And you know that from your operating systems course, that a blocking command is where your process is blocked until the input or output it is waiting for has occurred. Socket, bind, and listen are not blocking commands, but the accept is a blocking command. So when a server issues an accept command, it will be blocked. And that's why we say it is waiting. What is it waiting for? It's waiting for any client anywhere to connect to it. So it will sit there just waiting. If it's for hours, for days, if there's no client that wants to connect, it will just wait. So at the point that the client issues a connect command, remember we did last time the three-way handshake, that because of the unreliability of the internet, we need a three-way handshake. So when the client issues a connect command, an SYN message or packet will be sent to the server side. The server will be told that there's a client wishing to connect to it. And then the server will also send its own SYN with a sequence number. And then the client will send back an acknowledgement. I think that's what we spent a lot of time on Monday doing. So there will be a three-way handshake, and then both sockets will go into the established state. But of course, we said if there's any problem, then there will be that reject command or the reset. will be used to reject that connection. So as of today, we are there. So let me just move a little bit ahead, because today we want to look at the connection termination, which is at the bottom. So I want to explain what the send and receive is about. Now, remember we've said that when two programs connect to each other, they create a connection, which is obviously a virtual connection. So it's a virtual connection between them. Now, once the connection is set and they've both gone into the established state, we said now they can begin the data transfer phase. In other words, the communication they really wanted to have, now they can have it. So any one of them can send data and maybe wait for a reply. Remember, it's a two-way communication channel. But normally, especially because we have a client and a server, normally the server does not initiate communication. The server sits there waiting for the client to say what it wants the server to do for it. So if it's a web server, for example, the client will be asking for web pages. And so the request will usually come from the client. Usually, you don't have requests coming from the server to the client. And this is important when you start writing your applications and you start converting your program into a client-server program. You have to now change your way of thinking. In the past, I've noticed students writing programs where the client, the server is sending a request to the client. In this way, maybe the client is supposed to enter some data, like in your case, I think you are entering information about books. And you find that somebody writes a program where the server is asking the client, enter the ISBN number or enter the title of the book. In other words, the request for the user to enter data is coming from the server, because what the person is trying to do, they want to enter data one by one. So they enter the title and they send the title to the server. Then when the server has received that, then the server says, okay, now enter the ISBN number. Now, servers don't behave that way. Servers don't make requests to clients. A server sits there until you tell it what you want it to do for you. So when you begin to write your programs, rethink how you're going to communicate with the server. Usually, the request comes from the client. The server only issues a reply to the request. So if you send, for example, the title, that is not a request. That is data you are sending. It's not a request. So think of what requests you need to have in your program to the server. You need to think clearly. And I have already put some reading material in the classroom, which I think by now you should start looking at. I have requested you to use several books there. Maybe I will need to look at it more carefully to guide you on this, but you need to start reading a little bit about client-server programs so that you understand what responsibility a client has and what responsibility the server has, so that when you're writing your program, you follow that model. You are now using a different model of programming called the client-server programming model. So you have to understand how that model works. But in a nutshell, as I'm saying, requests come from client and replies a server gives you only a reply. So for example, let me talk about the web browser, the web application. Usually you have the client, which is the browser, requesting for a web page. So by the time they are sending that request, they must clearly say which web page they want by giving its URL number. So once that request arrives at the server will look through its storage, get that web page, and send it back because that's what the client requested for. Okay. So we are at that point. So I was just about to say, once the channel has been created, they begin to communicate. Now, so if we use the client server model, we assume that the client sends a request to the server. So a request is sent to the server. When the request arrives at the server does whatever it needs to do so that it sends a reply. And when it has done that, it will send a reply. So if we look at this program, we assume that at a certain point, these two programs have connected to each other. I've lost my cursor. So at this point, a connection has been established. So the client begins by sending. So you notice here there's this arrow coming down from the command. So the next command in your program should be what the client program should send. So this will be the next statement after the connect statement. So the client, in between here, of course, your program will have to prepare what the client should send. But once that is prepared, then you use the send command and you give it what you want to send to the other socket. So the send command is executed and the transport layer, remember it's the transport layer that will do the sending. So you issue the command from the application layer, but the transport layer does the sending. Now, once the send command has been executed, then the next command should be received, because if the client makes a request to the server, the next thing it expects is a reply. So this receive command is for receiving the reply that comes from the server. And of course, with that reply, there must be a buffer where you will put that reply. Now, so let's assume you're sending 10 GB file to the server. Then you'll have to use many send commands, because in one send command, there's a maximum size of data you can send. So obviously you will need to send and receive a reply, send and receive a reply, and so on and so forth. But you can iterate. Now, assume the client has several requests to make to the server. They'll have to send and receive a reply. They'll have to send and receive a reply until they are satisfied with the communication they've had with the server. So the sending is for sending a request or for sending data. Let's put it that way. It's for sending data or for sending a request. But usually in the client server model, you're sending a request. And usually the request is just one single message. And then you receive a reply, and then you send another request, you receive a reply, and so on. And when the client is through with that communication, then they issue the close command. The close command is the one that terminates the connection. Now, meanwhile, on the server side, from the time they issue the accept, and remember they had already created a queue. No, it will not be. Okay, let me put it in simplistic form because there's some information that I don't want to talk about right now. But let's assume that the server has a queue. It has a queue, not necessarily the queue that it mentioned here, but another queue we shall talk about later. So when the client sends a request to this server, those requests will be put in that queue. They'll be put in that queue, and the server will ask for those requests one by one. So anyway, after they accept, remember we said the program is blocked. So when a request comes in, then this program will be unblocked. And it will ask the transport layer to give it the first request in the queue. So it will use the receive. Receive is used for receiving requests. Send is used for sending data. So the first command after accept will be to receive whatever data. In other words, the transport layer will say, you have been waiting for something to come in, and now you have some information, so you can receive it. And so it will receive the message, and it will try to understand what it is being requested. If it's being requested for a web page or whatever it's being requested, it will get it, and then prepare it for transmission. And then once it has prepared it for transmission, then it will send it. It will send it to the client. And then it will go back to receive. Still on the connection, remember, still on this connection. So it will go back and receive on that connection the next request from the client. Then it will prepare the reply and then send the reply. And then go back and see if the client still has something to request for. And so this will go on between client and server until, in this case, the client has finished requesting for all the things it wanted to request. Now, notice that the close command is done by both the server and the client, because they both have to use that command to tell the transport layer that they are finished communicating and they want that, that connection closed. But usually, one side has to initiate it. One side needs to initiate the termination. But once the termination is initiated by one side, which is usually the client, if it's a client-server program, it will be terminated by the client, because remember, it's the client that approached the server and said, look, I want to communicate with you. So if it is finished communicating, it should ideally close and terminate that connection. So it will be initiated by the client, and again, we will have some kind of a handshake between them for reasons which I'm going to explain, because I said today we are looking at the termination of connection. So we are going to look at why does it need a three-way handshake, and what exactly are they exchanging, and why are they exchanging it. But I wanted to bring to your attention that this is really all you need to program a network program. These are the commands you need to know. So it will be good to think about them. If you can read ahead, fine. But if you find it difficult, just wait, I will explain. Okay. Any questions? Any questions? Did you follow what I explained, or maybe not?
We followed.
So you have no question? Yes, great.
I have a question. I'm seeing for closing, it
Mm.
is ideal that we close both the server side and client side. So this means, in let's say in my server file, there's usually a way I can access the client object, the client socket object. That means below I shall have two lines of code which will be closing server side and closing client side.
Say that again. Where did you get that from?
Okay, I'm just saying from I've been looking at the code for how to implement this in CPP, and there's the close function
Yes.
which you can use. And even in the server side, on accepting a connection, you
Mm.
can get the client details of the client which has connected to the server.
Yes.
Is it ideal, let's say in the server side, let's say I like when I'm closing the server, I also close the clients automatically, since I have the details of the client object, of the client socket. I have the details of the client socket, so I can do close
What
server
you
side.
have, what you have, Craig, is
Yes.
you have the address. Remember we said the connect command must put there the composite address, which is the
Yes.
IP address and the port number. So the once the client issues a connect to the server, remember we said that in the transport header, we put there the source port and the destination port. So when the message arrives at the server knows the source port. That is the port of the client. It knows whether it's port 10, 20, 100 or something. So it knows that. Remember that at the IP layer, we said that the other half of the composite address, which is the IP address, is passed down to the IP layer. So in the IP packet, the IP address of the sender is there. So on the receiving side, we would say that the server has both the IP address and the port number of the server, of the client.
Client.
Now, it does not have access to the port because the port issue is an operating system issue. Remember, I've told you that when you create a socket, it is the operating system that knows about that socket. It knows how many sockets have been created on this side. It knows what port numbers they are using. So it's an operating system issue, this socket. So when you issue the close, you are really telling the operating system. Remember that the TCP software is within the operating system. So you are really saying you want every record that the operating system has about this socket to be terminated or to be erased from memory. So that, for example, if you are using port number 90 and you have closed your socket, then any other program running on this machine can now be given port 90. So it's an operating system issue. This closing of the socket is an operating system issue because it will destroy all the records that the operating system has about the socket. So you seem to be suggesting that the server has direct access to this socket. It doesn't. What it has is the IP address or the composite address of the socket, which when it says to send, it can say, I want you to send this data to that socket. So then the transport layer will send that data, put the source port, and pass the IP address so that the packet will be addressed correctly to the right port. But this socket, this server side cannot directly access this socket. It can't. So what the close does, it does two things. One, as I said, is to make sure that the record of this socket is removed from the system. but it also needs to do a three-way handshake with the server, so that the server can know, look, the client has nothing more to send. Really, that's the idea, because the connection is open for data transfer. That's why we have three phases: open the connection, establish the connection, transfer data, and when you have transferred all the data you have to transfer, terminate that connection. So the close command is really to tell the peer, I have no more data to send. Don't sit there waiting for me. I'm not going to send any more.
I've understood. I've understood now.
Yeah.
Yeah, thank you.
Right. Unless you have any other question, I want to now go to the termination of the socket, or the termination of the connection, and what goes on. Yeah? Have a question?
Yes, madam, I have a question.
Yeah.
I'm trying to understand the roles of the send and receive functions. So we know that before connection is established,
Yeah.
three handshake process is there, whereby the server and the client exchange SYN and acknowledgements and those kind of communication for them to establish a connection.
Yeah.
So is the send and receive functions only used after the connection is established for the data exchange, or they are also involved in the connection setup?
Yeah, they have nothing to do with connection. By the time you start using send and receive, here you are in the data transfer phase. So this is the connection establishment phase, data transfer phase, and termination phase. Those are the three phases we said that any communication goes through. So send and receive means you have entered data transfer, which means they are only for data transfer. The reason for which you opened that connection. What did you want to say to your peer? That is what you say there. Is it clear?
Yes, yes.
Okay. So I believe I finished with the connection establishment. If there's anything I left, please read, and if you have any questions, you can ask. Okay. So either side or both sides may initiate connection. But if you're using the client-server model of programming, as I've said, it is usually the client that initiates it. It is under abnormal conditions will you have the server terminating a connection. Mostly it is the client that terminates or initiates the termination. But those commands for close can be used by either side. You need to know that. There is nothing to prevent the server if they wanted to use it, but they would be behaving like the client rather than the server. So, but remember that once the initiation has been done, the client is trying to get the mutual agreement. He's trying to get into a mutual agreement with the server that, look, we have finished communication. We need to close this connection. So the connection is usually closed by mutual agreement. And you shall just see in a short while why it has to take mutual agreement. Now, there are two styles of terminating a connection, the asymmetric or abrupt termination, or the symmetric or graceful termination. Now, typically we use the symmetric or the graceful termination. It's just like when you make a call to somebody. Usually, by the time you finish talking, you will tell them, look, I think we are finished talking. I need to go somewhere. You're trying to be graceful so that you just don't leave them hanging. You just, close the connection and you're gone and they're wondering what happened. So usually there's a graceful way to finish communication so that you both agree that, look, we have finished saying all the things we needed to say. But it is possible to do an abrupt termination. And of course, many times you've seen it when somebody runs out of airtime, you'll get an abrupt termination, but it leaves you hanging, because maybe you still had something to say. So even in communication, you can have abrupt termination, but it's not a good thing because you may leave the other side still wishing they could tell you something or they have more to tell you, but now you have terminated and you're not there to receive it. So even in network communication, you can have both types of termination, but the better one is the graceful termination. So the asymmetric or the abrupt termination is where one party disconnects the connection where one party, the connection is disconnected by one party. They make a unilateral decision to break the connection. So it's similar, as I said, to what may happen in the telephone system. It's even not normal, but usually one party disconnects. Now, in the symmetric connection, it treats the connection as a two-way channel, which it is. Remember, it's a two-way channel. The client can send and the server can send. So it's a two-way channel. So the symmetric connection treats the channel as a two-way channel so that each party closes their side of the channel, in the sense that if I am on a call with somebody and on my side I have finished talking or I have no more to say, I will tell them, look, for me, I have finished. In other words, I am closing my side of the channel and I'm telling them, don't expect any more communication from me. I'm done. But because the other side has not told me they are done, I am bound to sit there and wait until they tell me, even me, I'm done. So by doing that, they will also be closing their channel. The one they used to talk to me, they will be closing it officially. So in a symmetric connection, each side terminates their channel. So if this side is done, they will send a termination request, which means they have nothing more to say. But this side may still have something to say. So they have not closed their side of the channel. They'll keep sending data. They will just keep sending data. And if it's a telephone call, they'll keep talking. And since the other side had already closed the channel, they'll just sit there waiting or listening. So they'll send as much as they want. When they are done sending, then they will also send a termination command and say, look, now I am done talking. And at that time is when the connection will be closed. So this one had not closed the socket. Remember, there's only one socket. So they had not closed the socket because they were still waiting for the other side to talk. So even though they had finished with their side of communication, they were waiting so that they can now close the socket. Once this termination command comes, then now they can issue the close command. They can terminate. Similarly with this side, they had received a request from the other side to terminate the connection, but because they had not finished talking, they were still communicating. Once they have sent this termination request, then now they can close their socket. And that's what we call the graceful termination. So they are both in agreement that now we have finished talking. Now, the reason why we have this graceful termination is so that there is no data that is left that was not communicated. If we had had an abrupt termination at this point, and this side still had all this data to send, and maybe it had even sent it was still somewhere in the network, then you have lost data. In that communication, you have lost some data. And that's not the objective of communication. The objective of the communication is to be able to communicate and get all the information that was sent. So I've already used that diagram to explain what I wanted. Now, here we are going to look at an example of asymmetric termination, the abrupt termination. Now, as I said, the abrupt termination always has the possibility of losing data because it abruptly terminates the connection without knowing whether the other side still had data, especially in transit. The data may have been sent, but because it hasn't received, it has terminated without receiving that data. So if you look at this diagram here, you notice that here the connection was created. So this is connection creation and then the acknowledgement. So it's a two-way. This is a two-way handshake. And the assumption there is that the network is reliable. Then they begin to send data. So this one sends data and also sends data, but this data is on the way. When this side decides to abruptly terminate the connection by sending a termination command. Now, remember that this data is on the way. And by the time this data arrives, the connection has been closed. Now, that's what abrupt termination has the possibility of doing. So even though this side will close the connection, it will assume that this data it communicated arrived, when in fact it arrived after the connection had been closed. And that's why we need graceful termination, so that we don't lose any data that has been communicated and is in transit. So this slide just tries to explain that in written form. Now, so what we really want is not abrupt termination, but graceful termination. Now, in the presence of a reliable network, then you really don't need a three-way handshake, as I've shown in this diagram here. Here. You realize you only need two termination requests, one from the client to the server, and well, depending on which one is which, client or server, whichever way. But this one is the one that issues the first termination command. It arrives safely because the network is reliable. Then this one also finally sent the termination command and it arrives safely. So if we assume a reliable network, you really just need a two-way handshake. So we are going to see how that two-way handshake behaves, and then we will find out whether the two-way handshake can really be used when the network is unreliable. So the purpose of the graceful termination is to avoid data loss, as we said. So each side is released independently, and graceful termination prevents either side from closing the connection until all the data has been delivered. Now, to achieve this, a connection in the FIN wait state must continue to accept data segments until a disconnect request is received. Now, what that really means is this. When this side sends their termination request, they go into a state called FIN wait state. Why? First of all, this termination request that is sent is usually referred to as an FIN message. Just like we had the SYN, this is an FIN. I suppose it's short for finish. But in the termination request, you will set that FIN bit, which basically will be interpreted by the receiver that it's a request to terminate connection. And once the side has sent that FIN request, they will go into a state called FIN wait state. They will go into an FIN wait, which means they are waiting for an FIN from the other side. Okay? So to achieve this, a connection in the FIN wait state must continue to accept data segments, as we said. So it will still accept data from the other side until a disconnect request, another FIN, is received. And once it receives that FIN from the other side, it will know we are both done with this communication, and now I can terminate this connection. Of course, on the other side, it goes into another state. I think it is called the close wait state. We will see that in a short while. So I think on this side, when it receives the termination, it goes into a close wait state. I think it's called a close wait. Why is it called a close wait? A close wait. Because remember, we said that it is the application that closes the connection. Here, the close statement comes from the running application. Now, so really the other side is still in this data transfer phase. They're still in the data transfer phase. They are receiving data, they are sending it. They're receiving data, they are receiving data from the application and sending it. Of course, now they are not receiving. Remember, they are now not receiving because the other side has said they have no more data to send. So they are getting data, sending. They are getting data, sending, and they are not expecting anything to come back. So they are not using the receive. So they use this send several times to send the data that they have in bits and pieces based on the maximum size of the segment. And really what they are waiting for as they send is for the application to say it wants to close. So that's why we say they're in the close wait state. Now, on this particular side, the application has actually issued the close command. That side has actually issued the close command, but there must be some data sent between them. So this close is not yet done. The close has already sent the termination request, but it's waiting for the other termination. So the other side is actually here. It is in the fin wait state. This other side is in the close wait state. Okay, so now we look at the two-way handshake protocol with the assumption that the network is reliable. Now, so the two-way handshake on the initiator of the side of the initiator. We will look at both sides, the initiator of termination and the non-initiator of termination. So let's begin with the initiator of termination. In response to a TS user's close primitive, as I've explained, the application will have already issued the close command. So in response to that close request, a transport entity sends a disconnect request or the FIN segment to the other side, requesting for a termination. Now, having sent the disconnect request, the transport entity places the connection in the FIN wait state. In this state, the transport entity must continue to accept data from the other side and deliver the data to its user. So the data must be delivered to the recipient of now that's interesting. Okay, in this state, the transport entity must continue to accept data from the other side and deliver the data to its user. Yeah, I'm just thinking how it delivers it. So I need to think about that. So let me put a question mark here. But it continues to deliver the data to its user, because remember the receiver must receive data through the receive statement. So I'm just thinking of how it does the receive while it has issued a close. So when a disconnect request is received in response to the transport entity, then the transport entity informs its user and closes the connection. So it's just the way I'd already explained. So it goes into the fin-wait state, it continues to receive data from the other side, and it delivers that data to the application. Yeah, I need to think about that. It delivers the data to the application, and then as it waits for the other side to say, issue the termination command. And when that happens, then it closes the connection. When it receives a termination command from the other side, then it closes the connection. Now, on the non-initiator side, of course, it will receive a termination request, and it will inform its user that the termination request has been received, and then it will place the connection in a close wait state, as we said. In this state, the transport entity must continue to accept data from its user and transmit the data to the other side. Now, when the user issues a close primitive, then the transport entity sends corresponding FIN message to the other side and then closes the connection. So basically what I had already explained, only at the moment I'm not able to explain this, I need to think about it. Because really this request would not be sent. This FIN cannot be sent unless you have done a close. But remember, data is still coming in. So based on this diagram here, I'm just thinking how it will receive. Where was that diagram? This one. I'm just thinking of how or what is happening in the sense that it has issued a close command and yet it is still receiving data. I think that one I need to think about it. So just give me time, I'll think about it. Maybe there's something I've forgotten, but basically I'm describing the two-way handshake between the client and the server when they want to close a connection. As we said, it is done, you close each side of the connection, of the two-way connection, each side closes their part of the connection. And basically, it will work if the network is reliable, because none of the FIN messages will get lost. Now, so this two-way handshake procedure ensures that both sides have received all the data and that both sides agree to terminate. In other words, as we say, that's why we said it's a mutual agreement. They both agree to terminate the connection, and they are both saying, look, we have communicated everything we had to communicate, and if it's a response I required, I have received all the response that I needed. So this diagram, I think we saw it when we were talking about connection establishment. And now what we really need to look at is this half of the diagram, because I think we had looked at this part, the connection establishment. So now remember that by the time we did the connection establishment, they were both in the connection established state. Now, so this is the side that first sends the FIN. And we say the minute they send the FIN after the close connection, after the close command has been executed, they send an FIN and they go into the FIN wait state. This other side receives the FIN and goes into the close wait state. So this one is waiting for the application to issue a close. This one is waiting to receive the final FIN so that it can close the connection. So when the application issues a close, notice the application issues a close, then the transport layer sends an FIN to the other side, and this side goes into a closed connection state. When this side receives the FIN, it moves from the FIN state and goes into the closed state. And at that time, we say the connection is closed. So that's the two-way handshake state diagram and how the two sides agree to mutually close or terminate a connection. Now, things are a bit different when we are talking about an unreliable network, of which the internet is. And we find that the two-way handshake as defined is inadequate for when operating under an unreliable network service. Why? Because an unreliable network will have the following issues: misordering of segments, loss of segments, and even those segments that stay so long in the network and reappear at some later stage when things are now considered obsolete. Now, why are these issues problematic for the connection termination? Because if you have, for example, the misordering of segments, and we think of the the termination of a connection, it's possible, for example, to have sent a data segment or the last data that this one wanted to send, that is in the data transfer phase. Then after that, it sends an FIN to say, look, I'm done. And you find that this FIN arrives before the final data. And not just the final data, maybe there are several data that were sent earlier, and they're still making their way to the destination, because the network, of course, can allow data to follow different paths. But the FIN arrives before this data arrives. And then this side decides that this part of the connection is closed. And maybe it is also ready to close. So when it gets an FIN, it just also sends its FIN immediately. And the connection is closed. While this data here is still on the way. So misordering of segments can interfere with the connection termination. Similarly, lost segments. If some data was sent and it is lost, ideally it should really be retransmitted. But if the FIN arrives before the lost data, then you find that the connection is closed. And yet there's some data that has not been received. Now notice that in the two-way handshake, the FIN does not have a number. The FIN has no number. There is no need for a number there. So it's just an FIN with the FIN bit set. So the receiver has no idea what was the last data segment that was sent. What was the sequence number of the last data segment which was sent? It was not told. It doesn't know, because once the connection is established, and you had already said we are starting at sequence number 0, there's no way for the server or the recipient to know how many data items you want to send. You didn't agree on that. You just said where you are going to start from. So you can send from 0 to the last number. You can even wrap around, start again from 0 to the last number, and so on. This side has no idea how many data segments you want to send. So when it receives an FIN, all it knows is that you have finished communicating. Right? So these problems here can interfere with connection termination. And the connection can be terminated whilst there's some data that was sent and was never received. So this is just the explanation of why those problems that arise from an unreliable network are important. A transport entity in the closed wait state sends its last data segment followed by an FIN segment, but the FIN segment arrives on the other side before the last data segment because they arrive out of order. The receiving transport entity will accept the FIN, close the connection, and lose the last segment of data. So data will have been lost, yet it was communicated. Now, with the possibility of lost FIN segments and the lost FIN segments and the delayed or obsolete FIN or data segments, you have those similar problems that we had with the connection establishment. Remember that an FIN was, an SYN was arriving in the middle of a connection. It was arriving after the connection was established and connection was terminated, then it arrives. So we have the same problems here. So assume that an FIN is delayed. You already opened that connection, you communicated and you closed it. And you opened another connection and now you're communicating, and suddenly an FIN that is obsolete arrives in this connection. And remember, it has no number. It has nothing to say it is from another connection. So it arrives in the middle of this connection and it says, look, I want to terminate the connection. What do you think the other side will do? It doesn't know. So it will begin to terminate the connection. So once data begins to come, once data comes in, it will just say, but you told me you wanted to close. So it will just drop the data. So all those issues we talked about when I'm talking about the connection establishment, they will happen when you have lost and obsolete FIN segments still in the network. You will have the same problems. So we cannot do connection termination with two-way handshake in the presence of these possibilities. Because as we said, we lose data, we will have situations where we are prematurely disconnecting, and it's not what was intended. So, in the presence of an unreliable network, two-way handshake may just be okay as long as you had agreed on how much data you want to send. So if I go back to this diagram here, I said you opened a connection, you never communicated to the other side how much data you want to send. But if perchance you had communicated and said, me, I only have 8 data segments to send, then once this side has received the 8 data segments and it receives an FIN, it will know the communication is over. Or even if the FIN arrives before all the data has arrived, it can wait because you had already said, I will send you 8 data segments. So connection termination can only occur in the presence of an unreliable network if there is prior agreement on how much data you need to send. In that sense, maybe it can work, but under normal circumstances, it doesn't work because really you have no idea how much data was to be sent. So only if there was a fixed amount of data that was agreed upon beforehand. Otherwise, the protocol does not work. So we have seen that with a two-way handshake, all you need are 2 messages. You send the FIN and you receive the FIN, and you close the connection. But where you have possibility of losing data, it's very difficult to come to this agreement. And I want you to think about this problem here called the two-army problem. I don't know if you've come across it. But just think about this problem. Now, here are two armies. Let's call one the blue army and one the white army. So here we'll call this the blue army. Now, the blue army is separated by this valley here. Here is the white army. Now, what the blue army wants to achieve, remember, notice there are four in the blue army, but they are separated. We have two on this side, two on this side. So if they join forces, they can fight the white army and win, because the white army only has 3 soldiers. So what the blue army is trying to achieve here is to agree. They want to agree, let us attack. Let us attack at a certain time. So maybe they want to agree at 9 p.m. or at 9 a.m. Let us all descend into the valley and attack the white army. They want to come to that agreement. Now, the problem they have is this army is in the valley. So if they send a message to this side and say, can we attack tomorrow at 9? Of course, they expect a reply, say, okay, we agree, let us all attack at 9. But the messenger they will send will have to go through this valley. And if they can dodge the white army, they can be able to send the message to the other side. But there is no guarantee that they will be able to avoid this army or dodge them and get to the other side. So they may be captured. The messenger may be captured, and the messenger is not part of the army, remember. So they can send a messenger who may or may not be captured by the army. If they are not captured, they will deliver the message. If they are captured, the message will be lost. So the question is, can they reach an agreement? Do you think this blue army can reach an agreement where they are sure that they have delivered the message and they are all both going to attack at 9? Because if they don't reach that agreement, one side will attack, but they will be overpowered because they are only 2. So think about it. Do you think they can ever reach that agreement with certainty? What do you think? Because this takes us back to the mutual agreement to close the connection. They want to reach a mutual agreement to close the connection. Can they be sure that they have closed the connection? That's really what we are driving at, but we are using this problem to see whether or not that agreement can be reached in the presence of an unreliable network. Anybody with an answer? Yes, go ahead. Ansel?
No.
Was it Hassan? Hansel or Hassan, whoever is ready, just go ahead. What do you think?
I would say they can never reach.
Why? Why do you think they can never reach that agreement?
Because there's at any given time, there's no one army that can be sure if their message has reached the other.
Good. Really, that is the answer. That is really the position. Think about it this way. So this side sends a request to the other side saying, are you ready for us to attack tomorrow at 9? So they send their request to the other side. And let's assume the request arrives and this side says, look, we are ready. So they are replying and saying, we agree, let us attack tomorrow at 9. The question is, who really knows whether the agreement has been reached? Because remember, they are aware the White Army is there. So when this one sent their request, were they sure that the request arrived? They would not be sure until they have received the response, because there's a possibility that the guy was captured. So they will be waiting for the response for them to be sure that actually the other side got the message and they're in agreement. So by good luck, they receive a response. And so they say, yeah, the other side has agreed. But now this side is in the same dilemma. We sent them a reply saying that we have agreed, but are we sure they really got it? Because we might find ourselves in the valley, just the two of us. So for them, they are not sure the reply has arrived, so they are afraid to attack because they might end up just being two. So they would need another reply for them to be actually certain. They would need that reply. But now once this one send a reply, they will also be doubting, did they really receive? And so there is really no answer to that. There's really no end to that, where they can be certain that if we attack at this time we have agreed, we will overpower this army. Okay, so really what are we saying? That once we have this unreliable network scenario, it's really difficult to reach that agreement so that we all close the network at the same time. Remember that in the two-way handshake, this one goes into the fin-wait state, and when it receives the FIN, then it closes. So, but they're actually closing the connection at the same time. Because once this one sends the FIN, they also close the connection, and this side also closes its connection. So that's what we are saying. It's very difficult for them to achieve that in the presence of an unreliable network. So really what we need is a situation where each one of them they have that graceful termination. I'm done. Are you done too? The other one responds, I'm done too. And then they say goodbye. We're already in the three-way handshake scenario, which we have even said is not even possible. Even with the three-way, you still won't get that ability to close at the same time. So what is the solution? Now, I'll give you a series of solutions. I think there are about 2 different solutions to this problem, which when combined will give us a different scenario. So in the question of the data getting lost and the FIN arriving before the data, we can introduce a sequence number. So we introduce a sequence number in the FIN. Remember, the FIN did not have a sequence number. It did not need to have a sequence number. The sequence number was for the data. But now, because we are realizing the FIN can arrive before the data, we are introducing a sequence number so that if the last data item has sequence number 8, the FIN will have a number following that, so that you always know if there's some outstanding data that was sent before the FIN. So for example, if this side was sending data from 0 to 8 and then an FIN of 9, if any of the data, maybe they have received from 0 to 5, and 6, 7, and 8 are outstanding, but then suddenly they receive an FIN with number 9, they will know to wait for the data. They will know that there is some data that has been sent, so we have to wait for data up to number 8 before we execute this FIN. So usually the FIN is given the next sequence number after the last octet. And if I haven't said it, I need to remind you again, data in TCP is sent, what is numbered are the different bytes. Remember, a byte is an 8-bit number. So each byte is numbered. So, which means that the FIN will get the next number for the next byte or the next octet. So as I mentioned, the sequence number will solve that problem. Now, with the other one, we say the same problems that arose in the connection establishment will still arise here. So how do we solve that problem? So each side must explicitly acknowledge the disconnect request of the other side. Just like we said for the connection establishment. You must acknowledge the connection termination request from the other side. Now the FIN ACK, the acknowledgement for the FIN contains the sequence number of the disconnect request to be acknowledged. I think it's really an increment. You increment it by 1. So if one side sends a disconnect or an FIN request with sequence number I, then the response will have acknowledgement I plus 1. So it must send a disconnect FIN with I sequence number and receive an acknowledgement with I plus 1. Now the other side, of course, will receive, I don't know why I'm mixing these things. Now the other side, of course, will send the disconnect request with sequence number J and will receive an acknowledgement with J plus 1. So notice that these are 4 requests. These are 4 different FIN statements or requests. So you send a request, you receive a reply, and you terminate your side of the connection. Because remember, the first FIN was for terminating this side of the connection. And now we wait for this side to send their FIN and also receive an acknowledgement. So really there are 4. So it should really be a 4-way handshake. But it can be shortened to 3-way because remember that this request here and this request here can be combined. So you can end up having a 3-way handshake, but ideally it's a 4-way handshake. And notice that after you have received those 4, you still must wait an interval of time equal to twice the maximum expected segment lifetime. And this is to allow for that situation where data may get lost. So even after they have agreed to terminate the connection, remember that each side cannot be sure that the other one has received. Maybe if this one was the first, it will be sure that the other has received, but this last one is not sure. So they have to wait around. They have to wait around for some time, because if this one times out because it has not received, it may send another FIN. So you just don't receive the final FIN and send your acknowledgement and then terminate because you're not sure if this one will arrive. So you hang around for some time interval to wait and see if the other side will time out, because there will be a timeout, and retransmit the FIN to say, look, I really want to close and I'm waiting for your response. So if that happens, of course, you retransmit the acknowledgement. But there is that waiting period where you wait to ascertain that the other side has received. But notice it's not foolproof. It's not foolproof because even this side may transmit that request and it may get lost on the way. So once this one waits for that interval of time, it will just close and assume that the connection is closed. So if things happen that way, then this side will be left hanging. If at all it didn't receive the reply, it retransmitted the request never got there, it is waiting for a reply, it will be hanging. So that's usually called a half-closed connection. So it's possible in an unreliable network to have what we call a half-closed connection because of the problems of lost segments and so on. So it is really not foolproof, but at least you have made an effort. So really what we have is a four-way handshake. So the connection termination phase uses a four-way handshake with each side of the connection terminating independently. Now, when an endpoint wishes to stop its half of the connection, it transmits an FIN packet with the other end, which the other end acknowledges with an ACK. So it's a four-way handshake, and each side transmits their FIN packet and waits for an acknowledgement. So basically, it's a four-way handshake for the connection termination, for each side to close their side of the connection independent of the other one, because we said you cannot be sure the other side has finished talking. So once you close your side of the connection, you receive your ACK, you wait for the other side to continue sending data until they are ready to terminate. Then they will send their FIN, and then they receive the ACK. But notice that you can actually send both the ACK and the FIN if you are actually ready to terminate. So that will be the four-way handshake. You send the FIN, you go into notice the states. So the initiator sends the first FIN and goes into the FIN wait stage number 1. Then the other side receives the FIN and goes into the close wait state and then sends back the acknowledgement. When the acknowledgement is received, the initiator goes into the FIN wait stage 2 because it's still waiting for an FIN. The FIN stage wait 2 is basically saying, I have been acknowledged. My FIN has been acknowledged. The FIN wait state number 1 basically says, I have sent an FIN, but it has not been acknowledged. Now, when the other side, the receiver, is ready to terminate, they send their FIN and go into a state called the last ACK, which means they're waiting for the last acknowledgement. So they send their FIN and go into the state called last acknowledgement, waiting for the acknowledgement. The side that receives that FIN then goes into the time wait stage. Remember, we said there's a time interval which it waits for, so that it knows whether the other side has actually received. So it moves from the FIN wait stage number 2 and goes into the time wait state. And then it sends the acknowledgement. When the other side receives the acknowledgement, now it goes into the closed state. But the other side is still in the time wait scenario. And we say that in case this last ACK gets lost, then this receiver can still send their last ACK again. They will still remain in the last ACK state and send that last FIN again. And because this side is still in the time wait state, it can send the acknowledgement again. But if the time wait state expires, then it goes into the closed state. But if everything works correctly, then they will both of them go into the closed state. So that this other diagram is basically saying the same thing. You can look at it later. I think it is still just saying the same thing. Now, it is also possible to terminate the connection by a three-way handshake when host A sends an FIN and host B replies with an FIN stroke acknowledgement. That is possible. If A sends the FIN, and the other side is also ready to terminate, it will send one message with both the FIN and the ACK. Remember that in the header of the transport segment, These are two separate bits. The ARC bit and the FIN bit are separate. So all you need to do is to set them so that now the receiver knows it's both an acknowledgement and an FIN. So there's nothing to prevent one side from combining those into one statement. So it's possible to have a three-way handshake when host A sends an FIN and host B replies with an FIN and ARC, which combines those two steps into one. And then host A replies with an acknowledgement. So you can have this three-way handshake. FIN plus ARC and that. Now notice what may happen. FIN and acknowledgement is just to close one side of the connection because it's a two-way connection. So that closes this side of the connection. But this side may still have data to send, and it may continue to send data until it is ready. Then when it is ready, then it sends its last FIN and get an acknowledgement. So just because it receives an FIN does not mean it stops sending. It may still have data to send. And this side is obliged to wait for that data so that no data is lost. Okay, so basically I think we have looked at connection termination and connection establishment, and you can always look at these diagram. Notice that in this diagram we have a lot more states than in the two-way handshake. I've already explained them, so you just need to take this diagram and look through it and notice the introduction of the two fin weight states before you go into the time weight state, and then before you go to the close state. This one goes from the close weight to the last arc and then to the closed state. Yeah, it goes to the closed state, I believe. Yeah. So you just need to look at this diagram and interpret it in the presence of what we have said, and you will realize that you understand. So now I believe you understand this diagram a little bit more. The one we started with. Remember, we started with this diagram. So I believe that you are able to appreciate what's going on here. Now, remember, I could have started the programming class by just teaching you these things, but you may not have understood what's going on underneath. And that's why I've chosen to do the transport layer so that when you start writing your programs, you know that there's a lot more going on at the lower level, because at your program, you won't know there's a three-way handshake. You will not know all that is going on. You will not even know, there are many things you won't know. So it's good for us to understand it from the transport layer side so that when you start writing your programs, you appreciate what's happening underneath. So I think that brings me to the end of the connection establishment and connection termination, unless you have a question. Now you can look at these diagrams at a later time to appreciate, or maybe we look at them next time, but look at them and try to appreciate what's happening. I believe you will be able to understand them, because now this diagram starts from the very beginning, the connection establishment phase, then the data transfer phase, then the connection termination phase. So it puts all those things together in one diagram. And I believe that from what we have said, you will appreciate what will be going on when your program is running. So any question, and please make sure you look at them. We'll briefly look at them in the next class, and make sure you can answer these questions. And make sure you look at the past papers to look at the possible questions and see whether there's any question there on termination. If you can answer them, that would be good. And remember, I've already set a date for the CAT, which is on the 3rd. So all the things we'll have done up to the 3rd will come into the CAT. Will come in the CAT. So any questions? Any questions? I'll take it that you have followed what I have explained. So, yes, Jerry, and you had a question from last time. I waited for it. I never saw it. But anyway, want to ask a question?
No, it was in regards to that question. I sent it to your email yesterday morning.
Yesterday, I didn't look at my email because I had a class yesterday, so most likely I didn't see it, and I haven't seen it up to now.
Okay, but I
But I
can
can check my email and see the question. Let me see where it is. Okay, yeah. Right, let me try and read it and see whether I can follow it. So, following up on our discussion in class, I wanted to explain my question in detail. You had said that the three-way handshake prevents the problem of obsolete data segment arrives after connection is closed and a new one established. So that is the scenario you are interested in. By selecting a sequence number that is far removed, the obsolete data segment arrives after connection is closed and new one established by selecting a sequence number that is far removed from the sequence number of the previous connection. That's correct. My question is, apart from using the sequence number that is far removed from the previous connection, can one also say that the server will identify that the connection is wrong by the contents of the SYN segment sent by the client? For example, the client sends an obsolete. Now, remember, the client doesn't send an obsolete segment. The segment becomes obsolete. I'm answering your question, Jerry, but I've stopped at this point. You don't say that a client sends an obsolete segment. A client always sends a segment at a particular time. It becomes obsolete because it has stayed in the network for too long. And it arrives when the function it was supposed to perform has already been done. And in that case, it is considered obsolete. Okay? So anyway, you say that. Can one say that the server will identify that the connection is wrong by the contents of the SYN sent by the client? For example, the client sent an obsolete segment with SYN 401 and ARC Z+1. But the client expected, no, you can't say the client sends and the client expected. The client expected the segment to contain 401 and the correct sequence number of the server's SYN ARC, which may look as follows. My argument was that once the obsolete segment gets to the server, then perhaps the server will notice that the acknowledgement sequence number is incorrect and therefore send a request. Okay, there are so many things here that I'm not sure, but let me try and recreate the scenario because you're saying that the server will identify that the connection is wrong by the contents of the SYN segment sent by the client. Now, that's the part I don't understand, but let's do this. Let me stop here. Let me stop presenting and create what we call the whiteboard. That will give me space to understand this because I think you're talking about the client and not the server. I think you're mixing up the client and the server for some reason which I don't understand. So let me create this whiteboard here. So I want to recreate the scenario that you're talking about and see whether I follow your argument. I still don't follow it from what you've written because I think you've mixed up what the client is doing. And you're using the sequence number 401. So you tell me which part I am not understanding. So let me recreate it. So a connection has been closed, right? Jerry?
Yes, yes,
So a connection has been closed. And there's is it an SYN?
yes,
So an SYN appears out of nowhere, which was in the previous connection. SYN, isn't it?
yes.
It arrives here. Okay?
Mm.
Now, in the diagrams we had, remember that the client is also trying to create a connection. This client knows that this connection was closed and is now trying to create a new connection. The only problem is that their connection arrives after this one. That was one scenario. And maybe I should ask you which scenario you're talking about, because let me just stop sharing and look at the scenario that you're trying to, the scenario you think you are trying to talk about. So just a minute. So remind me which scenario exactly you are interested in. So let me go back. I believe it's in this set of slides that you have those scenarios. So tell me which scenario exactly it is you are talking about. So those are the scenarios.
Yeah, you
Is
just
that one?
passed it. No,
It's this one.
no. Just go ahead.
This one.
No,
This one.
after that one.
This one.
That one, yes.
Okay, so even let me just use this diagram. So a connection was established, some data was sent, and then there is this data with sequence number 401. Now here, remember, we are addressing the situation of an obsolete data segment. It has nothing to do with SYN. So that's why I'm saying you're mixing issues. This one is the obsolete data segment. It's some data that was sent in a previous connection, but it arrives in another connection. And because it has no relationship with this connection, it is called obsolete, because ideally this data was supposed to be received here. Okay? So since it was not received, it is now obsolete. That's why it's called obsolete. So it's arriving here, and in this connection, it is obsolete. Okay, so what happens here is that this data arrives before this one. You must realize that this diagram is a time sequence diagram. Time increases in that direction. So this one arrives before this one. And we are saying that because it arrives before, it is actually taken in as being what is expected. Because remember that the receive window is saying we expect sequence number 401, at least it's in the receive window. So it is received. Now, when the actual 401 arrives, it is discarded because the window has been slided in the forward direction. But I think your question is more about the three-way handshake. How does the three-way handshake deal with this situation?
Yes.
Yes, how does the three-way handshake deal with this situation? We said about the number far removed, as the connection was created with numbers far removed from what was in the previous connection. So let me just make one assumption here, that the sequence number that this one started with was 0, and of course it was acknowledged with 1, and so the sequence number started from 1. So it has sent data, and here it was trying to send a frame with bytes starting from 401. So we assume that each frame contains 200 bytes. So since this one is starting from 400, we assume it's 401 up to 600. So each one of them is carrying 200 bytes from what we can see here. Now, whatever happened, we don't know. Maybe this connection was closed abruptly or whatever, but it was closed. And now this side has opened another connection. And in the two-way handshake, there was no requirement to start from a number far removed. But in the three-way handshake, this would not have happened. So maybe this number was going from 0 to 600. Let's just make that assumption, from 0 to 600. And then we are saying that because it knows that it created a connection and gave a sequence number 0, and it knows that it used the sequence numbers up to 600. Now it will, of course, it doesn't do it. The operating system actually does it. So the operating system will give it a number, sequence number far removed. So let me just assume it takes a sequence number 10,000, far removed from that one, right? Jerry, you're still with me?
Yes.
So it's in the three-way handshake, this would have started with a number far removed. And then if we assume this is a time sequence diagram, this thing would still have arrived here. And it would have arrived when this frame had been sent. And the one that was now expected was the next one that carries 400 bytes. So it would have arrived here. But what would have been the sequence number in this arrangement? The sequence number here would have been 10,001, 10,201, 10,401. So when this one arrives with the sequence number 401, there is no way it could have been accepted because already by here, it was at 10,201. It would have been at 10,201. So it would have known the next data to arrive will be the one with 10,401. But some sequence number arrives here with 401. It cannot be accepted. If it was a three-way handshake, it would have not been accepted. Now, you are saying that there's another way that the server could have known that this data is obsolete without using the sequence numbers, and that's the part I don't understand. So can you explain to me how you think the server would have known that this 401 is obsolete apart from the sequence number?
Okay, I was assuming that for every data segment that is sent by the client, the server sends an acknowledgement back.
Yes, it does.
And in that acknowledgement, there is the sequence of the acknowledgement and the sequence of the next expected data segment from the client, like X+1.
Okay, so let's assume what acknowledgement have been sent here. Remember that we are saying this data segment contains 200 bytes. So from here, it contains 200 bytes. So the acknowledgement would have said, I'm acknowledging up to 200. Okay, so the acknowledgement number would have been not 200, it would have been 10,200. In fact, it would have been 10,201, saying I have received from number 1,000 up to 200. The next number I expect from you is 10,201. So that the acknowledgement number would have been 10,201. And for sure, this side sent a segment starting from 10,201. Now, when it responds to this, because it has 200 bytes, it would have sent an acknowledgement saying, I have received up to 10,200. So the next number, 10,400. So the next number I'm expecting from you will be 10,401. And of course, it will be sliding its window. As long as they are acknowledged, it continues to slide its window. So that would have been the acknowledgement. So now tell me, how would this acknowledgement have helped?
Okay, so I thought like inside the acknowledgement, there are two sequence numbers. The one for the acknowledgement itself, and the one for the sequence number for the client, the one that they expect next. So I was thinking that if, for example, this obsolete segment comes and it has sent a scene with 4001, and perhaps inside that scene there is an acknowledgement for the previous connections server, which, for example, if it was a certain number X, but then the server sees inside that obsolete segment, the acknowledgement portion is wrong. So will
Just
it?
hold on. Just hold on. Just hold on. Now, differentiate between what you are calling scene and sequence number. Is this what you are calling scene, or this a sequence number?
No, that's the scene.
SYN.
Yes.
This is the sequence number.
Mm.
This is the sequence number you put inside the frame. So let me take you back to the header, transport header. Transport header has a source port and a destination port. Then it has a sequence number, the sequence number of the packet or the segment, and an acknowledgement number. Okay, we are together?
Yes, yes.
There's a sequence number and there's an acknowledgement number. So now let's go back to our diagram. So this SN is not SYN. It is a sequence number. Okay?
Okay.
So by the time this data is arriving, the SYN has already created a connection. And even if there was an SYN still floating in the network, it would still come. An SYN could still come, right? It is still possible,
Yes.
but let us deal with one problem at a time.
Yes.
Let us deal with one problem at a time. Let us deal with the issue of the SYN appearing from nowhere, separate from the data appearing from nowhere. I think those are two different issues. Or you want to mix them?
No, let's just deal with the data segment first.
Okay, so if we are dealing with the data segment first, remember that this side will number its data. It will number them, it will sequence them. So the first sequence, of course, will be 10,001. 10,000, because it said it was starting from 10,000. So the first data segment will have 10,001, and inside it will be carrying 200 bytes. So that will be the sequence number. It may choose to put an acknowledgement, but typically if this side does not send anything, it will be a one-way communication. So there's really nothing to acknowledge. So in the acknowledgement, it will just put what the sequence number of this one was. So let's assume the sequence number of this side was 700. Let's just assume. Let's assume it has data to send, but it hasn't sent. So inside this segment here, the sequence number will be 10,001, and the acknowledgement number will be 700, which means I'm 700, and which means I'm still waiting to receive data from you starting from 701 because it hasn't received. So that's what will be in this segment. So when it comes here, this side will receive the 200 bytes and say, look, I'm acknowledging that I've received your 200 bytes. And now I'm expecting the next segment to have 10,201 as the sequence number. Now, of course, this side will send an acknowledgement, but the sequence number will remain 701 because it has nothing to send. In fact, it really will not send any data. Remember that there is an acknowledgement, there's a sequence number for data, and there's a sequence number for acknowledgement. Since it has no data to send, there is no need to put the sequence number for the data it's sending. It will only put the acknowledgement. So the acknowledgement will say, I'm acknowledging the 200 bytes, and now I'm expecting from 10,201. So the next data will now contain 10,201 as the sequence number, And the acknowledgement will still be 701, which means saying, I'm still waiting for your first data item. You still haven't sent. So I'm acknowledging that I've received nothing from you. I'm still expecting number 701. So it will have in the sequence number 10,201 and 701 for the acknowledgement. So when it reaches this side, it will receive the 200 bytes and acknowledge. And in the acknowledgement, there'll be no data, so there should really be no sequence number, or it should be some sequence number where the other side will just know, look, I have not sent you any data. So the acknowledgement will now be 10,401, which means I'm now expecting data with 10,401 starting from. So this side will again send the third segment, sequence number 10,401, and acknowledgement 701. Now, in that process, you are telling me that the server can still know something.
Yes.
What will it know?
Now, for the sequence number of the data segment, if, for example, it still contains it's expecting 701, and then its own sequence number. Suppose the obsolete segment in its sequence number, it had the wrong server sequence number.
Like, give me an example.
Like it had 201, and then it says it was expecting, and its own sequence number is 401. So when it sends the message to the server notices that it's saying 201, but then the sequence number is also wrong.
So are you talking about this one here? This one here?
Yes.
So it comes with a sequence number what?
201.
And
then its own sequence number, which is 401.
Its own sequence number, which is 401?
Yes. And then now when the message arrives at the server side, it notices that the 400 is wrong. The 201 is wrong, sorry.
Yeah.
It's supposed to be 701.
Yeah. Yeah. Okay. All right. But you see, here, there are two windows. There is the receive window, which is the one concerned with this data it is receiving. This data should really be verified by the receive window. There is also a send window. There is also a send window, which shows what this side is ready to send. Okay? So the first thing that this side will look at will be whether this sequence number fits within its receive window. That's the first thing it will check. It will really not go by this acknowledgement, even though, of course, it will look at it. But let's just start with the sequence of the receive window. From this side, there's something it is expecting. There is something it is expecting data to start from a certain number. So when the data comes, the first thing it will check is whether it fits with it. Is it something it was expecting? Was it expecting data from the other side starting from sequence number 400? And it may find that its window is already at 10,401 going on forward. From 401 moving forward. This one arrives with sequence number 400, which is far removed. And already it will disqualify it before it even looks at the acknowledgement number. Now, the only time, now, of course, remember that this number here is both data plus acknowledgement. In case it is not carrying data, let's assume it was just an acknowledgement, and that will be determined by the bits that have been set. So maybe this thing was coming in and it is not even containing data. Then it will look at the acknowledgement part and say, okay, I notice you are not carrying any data. Perhaps you are just acknowledging some data I had sent you. So it will look at the acknowledgement. And again, it will go to its send window and find out which data did I send. Now, according to what we have here, it should be able to send from 701 going on, and it even hasn't sent anything. It has not sent anything. So according to its tables and records, it has not sent anything. But there's an acknowledgement coming in saying, and even let's say this acknowledgement was even 701 or even maybe 901. So it comes in as an acknowledgement for 901 because the data it would have sent would have started from 701 to 900. But it already knows it has not sent any data. It should have those records saying, really, I'm not expecting any data. I'm not expecting any data, any acknowledgement for any data which I haven't sent. So it cannot get confused to be confused that there's some data it had sent and now that data is being acknowledged.
Okay.
As I said, it always starts from the sequence number. And even if there is no data carried, the sequence number will be for something that had already been acknowledged before. So let us assume that this one had been acknowledged. It had been acknowledged, and so it was expecting the 10,401. It was expected to send 10,401, but it has no data to send, so it chooses not to send this one. What will be in the sequence number of this message? Or in the message that it sends, if at all it's supposed to be an acknowledgement? The sequence number should be 10,201. So even if it was just sending an acknowledgement, the sequence number it should put here should be 10,201, which is basically saying that was the last message I sent you. I have no new message to send. So it's really telling this side, the last message I sent you was 10,201. If you want to acknowledge it, you can acknowledge it, but that was the last message I sent you. I have no more messages to send you. So the expected sequence number here is 10,201. So when this message comes in, the first thing that this side will look at will be this sequence number. And when it looks at its receive window, it will find that the window has slided forward, and actually 10,201 was sent, was received, the data was received and acknowledged. So what it may do again would just be to send that acknowledgement again and say, look, I can see you are trying to say that you sent that data. Let me send you back the acknowledgement. And the acknowledgement would be 10,401. So it always looks at the sequence number. And the sequence number must match what is in its window. So what you are saying that somehow this can be looked at in isolation, I don't think that will happen. Both of them must agree, because it has a send window and a receive window. Any data that comes in must somehow fit within those two windows. I don't know if...
Yes. Yes, now I've understood. I wasn't considering the receive window and the send window.
They just have too much.
Okay.
When you have no data to send, you send the sequence number of the last data you sent. If you have no new data to send, the sequence number should just be the data you had already sent. And the other side, when it receives that sequence number, it will just respond with another acknowledgement. It will think that maybe you didn't see the acknowledgement. So it will just retransmit it again.
Okay.
Good. we stop there, and we meet on when? Monday? Yeah, Hassan and Felista.
Yes, madam.
Yeah. Yes, Hassan, you raised your hand.
No, no, no.
Felista, did you raise your hand? Okay, so we finish at that point. Thank you so much. Have a good day. See you on Monday.